We're going to take a look now at a topic that plays a very central role in chemistry, continuing throughout all the subsequent chemistry classes that you may take. This topic involves quantities in chemical reactions, or in other words, the relationship between quantities of reactants involved in a reaction, and these quantities can either be in mole amount or mass amount, and the quantities of products formed from these reactants, either mole or mass amount. So relationships between the various substances involved in a chemical reaction, if so much of reactant A reacts, how much of product B will form? This type of question is what we're looking at here, and there's a specific name that chemists give to this type of calculation. We call it stoichiometry. So stoichiometry is just a term that captures all that we are saying here. And sometimes it can be a little off-putting, all of these technical terms that we encounter in science, but I would actually rather use the word stoichiometry with you than trying to repeat this whole sentence again and again. So you will see me adopting it as we go through the rest of this problem and discussion. Notice this information in the Chem 2A text is found in Chapter 7, Section 7.8, and in the Chem 22 text, it is found in Chapter 8, Section 8.4. Okay, so stoichiometry involves examining relationships between quantities of reactants involved in a reaction and the products that can be formed from them. What sort of relationships? All types. And let's illustrate the idea of stoichiometry, or the concept, with a specific example, right? What I have up here is the balanced equation for the reaction of hydrogen with oxygen to form water, a very fundamental, very important reaction. If we were going to categorize this, I'd probably accept two placements for it. You could either categorize it as a synthesis or combination reaction, because you're forming a single product from two separate reactions, or two separate reactants, forming a single product. Synthesis, but I would also say you could call it a combustion reaction as well, because oxygen is one of the reactants. So you could say this is a combustion reaction of hydrogen gas with oxygen to form water. Either term would be fine. And then examining, we see that we needed to balance the equation by putting a coefficient 2 in front of the hydrogen and a coefficient 2 in front of the water. So here is our balanced equation, and now let's make a stoichiometry question and explore how to answer it. If 25 grams of oxygen gas reacts with excess hydrogen gas according to this equation, how many grams of water, the product, is produced? So this is what we're trying to figure out when we're doing a stoichiometry calculation. And although it's legitimate to say, well, who really cares? It's important to recognize that perhaps the biggest challenge we face as a planet, which is the challenge of not the coronavirus, although that's certainly a very immediate concern, but is the overall challenge of global warming, and how much carbon dioxide are we actually producing and putting into the atmosphere for every 1 tank of gas we burn in our car? Well, that question is ultimately a stoichiometry question. If you burn a tank of gasoline, how much carbon dioxide is actually produced in that combustion process and emitted, released into the atmosphere? So ultimately, stoichiometry questions need to have our attention and our ability to calculate and understand. So let's go back here to the example that we're looking at. One of my preferences when I'm doing a stoichiometry problem is to always take whatever data is given and try to put it in its appropriate place underneath the substance in the equation. So for example, I'm told that we're reacting 25 grams of oxygen gas. And there's plenty of hydrogen, so we don't have to worry about any problems with not enough hydrogen. Now that's a good question. What if there wasn't plenty of hydrogen? What if we had to worry about which one ran out first? Well, that's a sneak preview into our next topic, which is a limiting reactant problem, a limiting reactant stoichiometry problem. But we don't have to worry about that issue here because we're told that we have plenty of hydrogen gas. We don't need to worry about hydrogen gas running out. So if 25 grams of oxygen gas reacts, how many grams of water is produced in this reaction? That's a stoichiometry question. Here's the flow chart for solving stoichiometry problems. You must have the balanced chemical equation for the reaction. You cannot do a stoichiometry problem if you're missing that balanced chemical equation. In my class, that equation is either provided to you, I may give it to you, or you may be asked to write the chemical equation if it is one of the 5 types of chemical reactions that we were looking at. You should be able to look at the reactants, understand what type of reaction this is, and predict the products. So nomenclature skills are very important as we continue through this class, being able to write the correct chemical formulas for substances, understanding types of chemical reactions, knowing what type of reaction that you are looking at, and then being able to write the correct balanced chemical equation for the reaction. That is an important skill you need to develop. Why do we need that balanced chemical equation? Because we need the coefficients in the balanced equation. And those coefficients are giving us mole-to-mole relationships needed to calculate the quantity of a desired substance, whatever we are asked about. So this idea of mole-to-mole relationships that are coming from the coefficients from the balanced equation, we use these mole-to-mole relationships as conversion factors in order to solve the problem. For example, looking at the coefficients in this balanced equation, you recall that if no number is written in front of the oxygen, it's understood to be a coefficient of 1. Looking at this balanced equation, I can see that 2 moles of water is produced for every 2 moles of hydrogen gas that reacts. Literally reading this equation, we would read it as 2 moles of hydrogen gas reacts with 1 mole of oxygen gas to produce 2 moles of water. So these coefficients in the balanced equation are the mole-to-mole ratios or relationships between all of the substances involved in the reaction. So I have written 3 mole-to-mole relationships that are valid for this reaction. 2 moles of water is produced for every 2 moles of hydrogen gas that reacts. That is the first mole-to-mole ratio or relationship. The second that we can write is that 2 moles of water is produced for every 1 mole of oxygen gas that reacts. And here is that second mole-to-mole ratio written. And the last mole-to-mole ratio comes between the reactants themselves. 1 mole of oxygen is required to react with 2 moles of hydrogen. So I can write a third mole-to-mole ratio from this balanced equation. So we're going to need to use one of these ratios to solve this problem, specifically this ratio right here. That involves how much water is produced, 2 moles for every 1 mole of oxygen gas that reacts. So you must have the balanced chemical equation, and we do. Secondly, you have to follow a flow chart for solving the stoichiometry problem, and that flow chart is written in each of the sections that I've mentioned and also put up here on the board for you. Stoichiometry problems always will fit the same general pattern. You're told information about something. That something is called the given substance, what they tell you about. In this instance, our given substance is oxygen gas. We were told that there are 25 grams of oxygen gas that is reacting. That's the information that's provided to us. In this flow chart, you would take the moles of the given substance, you would take the mass of the given substance and convert it into moles of given substance, and we just studied how to do that in mole conversion problems. In order to go from mass of substance to moles of substance, you need the molar mass of that substance as a conversion factor. So we would use the molar mass of oxygen to convert from mass of oxygen, 25 grams, into how many moles of oxygen is present. But we don't want to know about moles of oxygen. We really want to know about water. So right here is the heart of any stoichiometry problem. You need to use the mole-to-mole ratio from the balanced equation in order to write a conversion factor to get you from moles of your given substance to moles of your desired substance. And in this instance, our desired substance is water. So the way I'm going to get from moles of oxygen to moles of water is to use a mole-to-mole relationship from the balanced equation, specifically this middle one here that gives me the relationship between water and oxygen. 2 moles of water is produced for every 1 mole of oxygen that reacts, and this relationship is coming right from the balanced equation. Coefficients involved. 2 moles of water produced for every 1 mole of oxygen that reacts. Once we use this mole-to-mole ratio as a conversion factor, we can convert from moles of oxygen to moles of water in this one-step calculation happening here. And then once you have moles of water, well, we know we can go from moles of a substance to a mass of a substance using the molar mass. So you can take moles of water, multiply by the molar mass of water, and calculate mass of water. And that's the overall flow chart. Sometimes we'll start a stoichiometry problem here with a mass that's given to us, or we can start a stoichiometry problem here. Oops, not here, sorry. Let me erase that and put this here. Right, we can start here with moles of given substance. In other words, you can either start by being given the mass of a substance, or you may start by being given the moles of a substance. You may be asked to calculate moles of desired substance, so you may be asked to end here, or you may be asked to calculate mass of desired substance. But you will always have this step. All right, you will always have a mole-to-mole ratio from the balanced equation. So you can start here in the problem, and in this instance we are starting with a mass of oxygen. You may start here with the problem. You may be given moles instead of mass of given substance. You may be asked to end with moles of desired substance. In other words, I could have said how many moles of water is produced. I didn't, but I could have, in which case we're ending here. Or you could be asked to solve for mass. So parts of this flow chart may not be involved, but you will always have the multimole relationship from the balanced equation that is involved in every stoichiometry problem. So just erasing here, we did not, or we do not have to go to or end with moles. We have to calculate mass of water in grams. So let's see if we can't put these pieces together and show the solution to the problem. 25 grams of oxygen, our given substance, is our starting point. That's what we're told. We now need to convert from mass of oxygen to moles of oxygen using the molar mass. And recall, of course, that oxygen is a diatomic molecule. So you need to look exactly at the chemical formula, not at any coefficients, but just the chemical formula, and add up the atoms in the chemical formula only. Do not pay attention to coefficients at this point, just the red chemical formulas for a molar mass. And I see there are 2 oxygen atoms in 1 molecule of oxygen, or 2 moles of oxygen in 1 mole of diatomic oxygen. So I'm going to write here using the periodic table and looking at the molar mass of oxygen, which is 16. 2 times 16 is 32 grams of oxygen for every 1 mole of oxygen. And our grams of oxygen are canceling here in the setup, and if I stop my calculation right now, I just calculated moles of oxygen. But I don't want to know about oxygen, I want to know about water. So right here is the heart of the stoichiometry problem. This is where we need that mole to mole ratio coming from the balanced equation. There are 2 moles of water produced for every 1 mole of oxygen that reacts. Right here, this mole to mole ratio, which is the heart really of the calculation. And sometimes, just to emphasize that with beginning chemistry students, I make a kind of poorly shaped heart here. This is the heart of the stoichiometry problem, this mole to mole relationship. If I look at the dimensional analysis, my moles of oxygen are canceling. Make sure you're labeling. In other words, don't try to take unnecessary shortcuts and forget to put the labels in, because that can confuse you whether you've written it properly or not. So make sure that you are labeling the identity of each substance. That lets you know what form to use the conversion factor. So my moles of oxygen are canceling, and if I stop my answer right now, I just calculated moles of water. And if I had asked for moles of water, we'd be done. But I asked for grams of water, and I labeled it here. So I see that I'm going to need a last step in the problem where I use the molar mass of water, looking at the chemical formula of water, H2O, using the periodic table and adding up the molar masses of 2 hydrogen and 1 oxygen. I come up with a molar mass of 18 grams of water to 1 mole of water. A question here about sig figs and molar masses. You need to use at least as many significant figures in your molar mass as in the data provided. So I see here that our initial data has 3 sig figs. So I'm going to use 3 sig figs for the molar masses of oxygen in water. In fact, I never use less than 3 sig figs in any calculation, even if the initial data does have less than 3 sig figs. I always use at least 3 sig figs. But if I had given you this data to 4 sig figs, 25.00 grams of oxygen, then you would have needed to use molar masses to 4 sig figs. So you correlate the sig figs of the molar mass with the sig figs of the data provided, but don't go less than 3 sig figs. So removing this 25 here with 4 sig figs, that's not what we're dealing with, and so don't want to confuse us with that, right? I can see that my moles of moles of water have canceled in the setup, and the last unit that's remaining is grams of water, which is what I'm asked to calculate. So taking your calculator, and I'm taking mine and going through, punching through the numbers. I call this a plug and chug step. You plug in the numbers in your calculator and then do the division here. And when I do the division, I come up with 28.1 grams of water produced in this reaction containing 3 sig figs for the answer. According to the setup, our answer should have 3 sig figs, and we just did our first stoichiometry problem.